Okay, so let's start the second half of our unit. Can I sit maybe right about here in the middle, perhaps? Does that work? The second half of our unit now is to actually start talking about the unit of energy. And when I talk about energy, I always like to actually start by discussing what makes something physics and what makes something chemistry. I may have given you this little spiel before, so I'm sorry if I'm repeating myself. Chemistry is all about the study of matter and how it changes. So when you learn about chemistry, you learn about the stuff in the universe, and you learn about its chemical equations, hydrogens and phosphoruses and all that stuff. Okay? Chemistry and physics are really closely related, though, because if chemistry is the stuff of matter, the stuff in our universe, physics is the study of matter plus energy. And that's why we're starting with energy. If you're comparing to, I know some kids are taking physics with Ray right now. He's going to teach in a different order than I am. He's going to do energy a little later in the year, but I like to start with energy because to me it is the fundamental reason why physics even exists. If we lived in a universe with only matter and no energy, we'd have no reason to do physics. Because energy is the push that gets stuff happening, right? Matter would be like your desk, this little board here, me and you. If we just had matter just sitting there, that's really boring. We want to get it in motion. And so there are two different types of energy then, two different ways that we can categorize our energy. And you probably already know this. The two forms are kinetic and potential. Kinetic is an active form of energy. I think that's actually the Greek root of the word. Don't quote me on that. But I believe like it refers to like the concept of things that are active and things that are in motion. Kinetic energy is things that are doing stuffs. That being said, we've also recognized that there are some forms of energy that are not active. They're more passive. And the better word rather than passive, though, is the word we use is potential. You've probably heard this one before, right? Potential is an energy that's waiting to happen as soon as we're ready. Right? Classic example, I drop an object. Right here is my whiteboard pen above the ground here. You all know what's going to happen if I let go. It's going to fall, right? And as I let go, it's now going to have kinetic energy because it'll be moving. But in order to get it to that stage, it has potential energy. It's stored and it's going to be used later. So gravitational potential energy is one of the most common forms of stored energy. Most every form of energy really falls into one of these two categories, active or passive. Now, we are only going to learn about a few of them in Physics 20, but you guys have probably learned about energy at a previous point, right? Like you guys heard about light energy, sound energy, chemical energy, nuclear energy. Right? You guys have heard of some of those different formats? Really, they either fall into they're actually currently being used, or we're about to use it in the future. Right? I would say that sound energy is more of a kinetic energy. Okay? I mean, it doesn't actually have a mass, but sound energy definitely involves the motion of vibrating particles. Right? So potential energy would be like the battery in your calculator. If your calculator is turned off, it has the potential to work once you press the button for on, but it's stored and wait for later. Now, before I talk about these formulas a bit, I really want to focus on the units of them. Okay? Have you guys seen these formulas in Science 10, hopefully? Kinetic energy is 1/2 mv squared. Potential energy due to gravity is mass times g times h. Okay. The first thing I want to spend some time discussing is this letter right here. We measure energy in joules. Okay? J stands for joule, named based on James Joule, famous physicist. Now, the reason why I'm spending some time on this is that I need to remind you that there are actually only 7 units in all of science, which some people will disagree with, but I mean, at its core, here are the main units in science. There's a mass, or let's go with that as meters. Then there's mass measured in kilograms. There's time measured in seconds. There is brightness measured in something called the candela. I think it's actually CD is how they abbreviate it. Moles is for how much amount of substance there is. Kelvins is for temperature. And what am I missing? Nope, because that's a hybrid one. Harrison, help me out here. What am I missing? I'm blanking on it. No, that's seconds. Shoot, which is the other one there? Amps. There you go. Okay, these are the 7 main forms of how you can measure a unit. Now, someone did kind of mention, joules is one of them. Well, joules is a hybrid of putting some of these units together. Every unit in the entire system of science is a hybrid of merging these 7 together. Let me show you this. Energy kinetic is based on mass times velocity squared. A mass is normally measured in kilograms. A velocity is normally measured in meters per second. And when you square it, you get 2 of them. Therefore, a joule is based on 5 units all smooshed together as some sort of Frankenstein hybrid. A joule is a kilogram times by a meter times by another meter and then divided by seconds twice. That is what officially makes it a joule. But isn't it a pain in the butt to write this every single time? Hence the need for an abbreviation. And many units that you're familiar with are abbreviations. A Newton, capital N for force, is an agglomerated unit. Capital T stands for Tesla, named after Nikola Tesla, and that's a measure of magnetic field strength. And so the stronger the magnet you have, the more Teslas there are. Same thing, it's based on kilograms and meters and seconds. Okay. Now let me prove to you why a joule can be found in different formulas. Hopefully you'll agree that this mass is in kilograms, and I did a velocity twice. But what about this formula down here? This is also energy, and so in theory it should also be a joule. Okay. M is mass, stands for kilograms. Do you guys remember what G stands for? Yeah. And we're going to spend a whole unit actually kind of talking about why we know gravity's number on Earth. But are you guys familiar with it being 9.81? And to be honest, I really dislike the fact that in grade 10, and to be honest, for me in grade 11 at first, I'm just kind of telling you, hey, trust me, it's 9.81. Because that's kind of unsatisfying. We're actually going to prove why it's 9.81 in multiple different ways. We're going to show you why gravity on Earth is 981. But for right now, is it cool if we just kind of know it's 981 and we'll get to the why later? Okay. Well, that's an acceleration, which means it's measured in meters per second squared. So I'm going to write it twice. So I wrote it twice. And then H stands for height. The further that something falls, the more energy it has. The analogy I gave this morning is imagine that you dropped a bowling ball on your foot from like 2 centimeters above the ground. That's not that bad. So you dropped a bowling ball on your foot from like 3 feet above the ground. That's going to hurt, right? The further the object falls, the more energy it's going to have. So hence height is a part of it. Now look at the unit conglomeration. I know that they're in a slightly different organized format because this was mass, velocity written out twice, and this is kilograms acceleration there. But don't we have the same 5 units at the end of the day? A single kilogram, 2 mass units, and 2, meters units, and 2 seconds units. And as long as they're in the right order, it makes it a joule. That makes sense? Okay, cool. You're probably familiar with these formulas, so why don't we fast forward and do some examples here? Because it's kind of silly for us not to just hop into some math equations. Okay. We'll figure out how much energy all of these objects have. Okay. So first example, there is a shelf in your locker 1.8 meters high. You have a textbook sitting in it. How much energy does that textbook have? Well, you might argue, Chris, there's a calculator sitting on my desk. It has no energy. Well, that's actually not true. It has gravitational potential energy. Not that I'm hoping that this would happen, but what would happen if the floor collapsed? All of us would fall down to the next level. We have potential energy, all of us, just merely because we're on the 2nd floor. Does that make sense? And so does this textbook in your locker. So without beating around the bush too much, hopefully you can handle this. Your gravitational potential energy is mass times gravity times height. The mass was 1.2. Gravity, 9.81. By the way, I need to point something out here. That gravity number, though, is only on Earth. Does that explain to you guys when you learn that number? The gravitational amount on the moon and on Mars and in other places in the universe, it's a different amount. But in general, most locations on Earth are 9.81. If you were to go to the top of Mount Everest, though, it's like 9.6 or 9.7, by the way. The higher up in altitude you go, the less gravity there is, which you may have already known anyways, because when you're in outer space, you ever heard how astronauts are weightless in outer space? The further away from Earth you get, the less gravity affects you. So in general, most places on Earth are 9.81. So, okay, and then your change in height is 1.8, right? So I don't even need to algebra this. I just need to type numbers into a calculator. 1.2 times 9.81 times 1.8 is 21. 0.1896 joules. However, this is what I've been trying to teach you guys for the last week and a half here, is that although your calculator spits out the number 21.1896, that's not a good number for you to write down on paper. I mean, again, we're only in grade 11 physics, but like think about this as like you're publishing some sort of research that you just did there. I cannot guarantee that this number is a 6. I can't. I can't guarantee this number is a 9, or even that this number is an 8. Based on the digits that I have here, this has 2 sig digs, this has 3 sig digs, this has 2 sig digs. I got to stop this at 21. That's all I can guarantee. And that same logic really applies to the 9.81. Depending where on Earth you are, it actually could have been 9.811. It could have been 9.807. It really depends where in the world you are as to what the gravitational value is. But on average, it averages out to about 9.81, so that's why we go with that number. But it depends on where you are above sea level. So far so good. Question 2. Okay, here's a car, got a mass of 1,500 kilograms, moving 100 clicks on the highway. Does this have potential energy? Well, if it's driving on an overpass, maybe. If it's flying, that'd be cool. Chances are we're talking kinetic energy, though. So your kinetic energy formula is 1/2 mv squared. So you do 1/2 of 1,500, and you times by your velocity, which is 100, and you square it. Except I did that wrong. What did I do wrong? Go for it. Close. It's actually not grams we want. We do want kilograms. But you do want this to be meters per second. Yeah. And the reason why I illustrate this point, this is really key, is that if you wish to use units like joules, which are so convenient, you have to make them up using the right components. And so a joule is made out of kilograms, meters, and seconds. Sorry, that's my total, I guess. So if you're not using the right unit, you can't call it a joule. You could, in theory, multiply these numbers by each other, and it would get you an energy amount, but it wouldn't be in joules. It would be in some sort of random, weird unit I've never heard of before. Right? So you have to convert. Did I show you guys the shortcut conversion for meters per second and kilometers an hour yet? It's 3.6, if I haven't said that. So if you just divide by 3.6, you'll get an answer. Now, you could do 100 divided by 3.6 and get 27 something. Or I like to do it right here. I just make it 100 divided by 3.6 right in the question, because I like that. That's much neater, and it's like rather than doing 2 steps, I'm just doing 1 step. So anyways, for what it's worth, you're doing 1/2 of 1,500, and then your 100 has to divide by 3.6 and then square it. And you get this answer here. It's 578. 703, basically. And now we need to round it. I cannot guarantee this number being a 3, right? Like, that same problem of precision. But this particular question is going to require a little bit of reading between the lines. If someone is traveling 100 kilometers on the highway, do you think that this was actually the number 55 and we rounded it up generously up to 100? I doubt it. I feel like it probably actually was the number 100, right on the dot, probably. I mean, maybe they rounded to the nearest tens, but this number right here, I'm not sure how many sig digs this has. This could have 2 or 3 or 4 sig digs, because this number could have been rounded to exactly the ones, or we might have said, it's about 1,500 kilograms. In the same way, if I were to ask you how much money you have in your bank account, you might have said, I have about $300. Do you have exactly 300.00? Probably not. You probably rounded. So my gut feeling here is that if you were to weigh a car, what are the chances that it was exactly 1,500 to the exact kilogram? Probably not. So my guess is it probably was 2 sig digs. But there's some leeway on this one. We're not 100% sure because I don't know who measured it. This is the best I can guarantee. I think the best I can say is that it's 5 times 10 to the 5. Move that decimal place over 1, 2, 3, 4, 5 times. Round the 7 up to the 8, and that is the best that I can say with certainty. With accuracy, that's all I'm willing to stake my reputation on. Is that a good way of putting that? You're fine. If If you're wrong, you want to make sure that you're not adding that extra digit. If I read an extra digit afterwards here, like 1, that would be wrong. Is that good? This one that we see in front is a baseball with a mass of 145 grams. Grams. What I'm going for here. And it's moving at a speed of something. Is that 10 or is that 18? Apparently it is. This has two different forms of energy. The object has kinetic energy. The object is above the ground, so it has potential energy. So we actually have to merge the formulas. And if I want to find its energy, it'll have some kinetic energy, due to 1/2 mv squared, and it'll have some gravitational energy, due to add both of them together. So it would be 1/2 of your mass, which is 145 divided by 1,000. Pretty simple with that. Like you have to convert your grams to kilograms. If you'd like to, make it 0.145 and just put a decimal place there if you'd like, that's fine. And then times by 18 squared. And then to that add mass, 45 over 1,000, times gravity on Earth, 981, times by the fact that it's 3.5 meters above the ground. And I'm going to do this more in our class. I don't actually hear this. Really feel the need to know that the answer was 17. Stop there and say, just type it in. Does anyone have any questions, though, about how I solved that? I mean, that was just literally adding forms of energy together. What if I have a slingshot? So imagine, I got a slingshot, I pull back from the slingshot. Is there energy? What sort of energy is the slingshot when you pull back on it? Kinetic? It has the potential to slingshot forward. So this means that we therefore need a new formula because that's not energy due to gravity. And as you're pulling back on the slingshot, it's not in motion yet. Okay. So one of the nice things about when you're learning physics is at a certain point, all I have to show you is basically here's a new formula, and here's what the letters mean. Right. This is a formula that is on your data sheet. I haven't talked about that yet. Does anybody have a formula sheet, by the way? If you have your formula sheets nearby, you want to take those out so you can follow the same thing. Let me know what your extras are. This sheet of all the formulas you're going to learn and sometimes it's fine if you don't. Intelligence is what is in the bottom. My right, the bottom left. The top one, second column. Square. The one below that is mg delta h. Mg. EP 1/2 kx. I'm going to solve the question first, and then I can show you the details of what it all means. 1/2 kx squared. All you need to know is which of these numbers is x. So I mean, when you solve it, I'm going to show you what the right answer is, and then I'll talk about why. It's going to be 1/2 of 156. This number right here is going to be what k is, and then x is going to be 6.8 divided by 100. Whatever that is, the answer. Okay, because if all physics is plugging numbers into formulas, there you go. You plug numbers into formulas. The first thing that you see in this new formula is the letter K. K. Spring constant. Anything that is elastic has a different flexibility. Kind of imagine that you were pulling back on some sort of stretchy elastic. There are some elastics really hard, just because they're a lot more. Another analogy I give is imagine that you're riding in the back of a car. You know how like there's shocks and struts in a car to help keep the car from springs up. Okay? And so that's what K is. K is basically constant. Force requires the A value. The harder it is to bend this slightly inflexible, have a very, very light. Then it requires like one. Something that compress it as well. Like if my fully inflated. Well, if you time-lapse video of that ball hitting the ground, you would actually see the ball a little bit squish. I'm actually going to put it on a black line around the ball. What happened right here is that there is this compression, and the ball is actually squishing. And then when that spring your so there's actually two ways. Or you compress it, but either way, it's going to try to. However, the extent that we want is not in centimeters, we want meters. So can you guys see why I divided this by 100 right here? And then the spring constant, one big doesn't really mean a whole lot to us. What I need you to know though is that the bigger the spring constant, the spring, is that a good word to use? The less the spring is. So far, so good. All of this was basically right. So much more than plugging. Emotion. All the hardest words. the object are not yet. Okay, let's talk about this. Backside. There are 10 big. Zero is uniform. We talked about that. Uniform motion is a type of motion. Very What if you were traveling in motion? Well, what could you be doing? Well, one, you could be accelerating. You're slowing down. Straight line direction. So principle number 2. It's still uniforming. And really, when you think about it, every usually all of a sudden have to all movement has to involve the 3 ways that that go on this sheet right there. Discuss right now. Well, work and describe to the kids. Move something in order for something to accomplish. Your inner stuff. Honestly, not that helpful. Where did you guys get your today? Processes there. But have a certain let's do a task. Talk more. I'm going to sit over here so I can see you guys better. Since work is defined in physics as a force causing an object to move through a displacement, I want to have to weird scenarios. Done on this just and the answer is 0. Work happens when you use a force and you sitting here. I wasn't. Are you applying a force? Why are you lifting your physics backpack up? What would cause it? If you are doing right here, I used a force to overcome gravity. But then if I move it this way, side to side, my force is holding it up, but it's going to... And although there is a distance, and it leads to then this next formula on your data sheet. The formula on your data sheet looks like this. W equals F. Only on use a big bar. Again, I got to tuck the little... Did you... Have you guys heard of that phrase up? Number -7 with 2 lines on top of it. It's still 7. Basically what it means. We don't care about any... Now here's why this matters in this formula right here. In the formula right here, the force has to be in the same direction as your distance. I don't really care if they're both negative, but if your force is going up and your distance is going to the side, you need them to be going in the same direction. And maybe a way of explaining this to you. What happens if it's kind of in the same direction? You're pulling on the box with your hand, but rather than pulling like... Actually, I have to pull this table right here. Even just think about the... Is it going to be easy for me to be in a bench approach like this? Or is it a little bit easier for me to use some leverage? A little bit. It's really awkward back on a straight line. So what if you're pulling... Well, now is that working? Really? Correct. You're going in... And the distance this thing is going to move is going to be along this leg right here. That's where the cos theta is. If you know your trigonometry, you guys ever heard of the SOH, CA, TOA? I want to focus on the CA. CA says that cosine of theta is the adjacent over the hypotenuse. There is a relationship, it's kind of a triangle right here, that if you're not pulling in exactly the same direction, that formula I just showed you. Work is equal to force times distance times cosine theta. What is the angle between you lifting up against gravity, but then walking down the hallway? What's the angle between these two? Never tried this before. Cosine of 90. Which means that if you have a force and a distance completely opposite, then cosine of 90 means you literally did no work. Even though you might have had a force of 50 newtons and you might have traveled a distance of 2, it really doesn't matter. What happens if you are just lifting an object up? So I'll use the same example here. But what if you were taking the object from the floor and lifting it up? So your force is going up, your distance is going up. Well, then using that same formula, force times distance times the cosine of theta, what is the angle difference between the two? Nothing. There is no difference angle between them because they're both going straight up. If you ever have a cosine of 0, cosine of 0 is actually 1, which means that we don't even need to have the cosine. And that's something in grade 10. A little cosine of theta, a little tag on it. Basic example now of how this might look different. It is a box. In this example right here, you use cosine 30. Here's my ground. Here's an object, a box, and the object is going to go. So you use your formula. The work that we do is force, and if you need, add on cosine of theta. Well, force was 8.1. So right here, 2.3 meters is how far you move it. Do we need the cosine theta bit on this particular example though? No. They're both the same direction. So because they're traveling the same direction, I can just omit this. If you want to, feel free. Type in cosine of 0. But cosine of 0 is 1. Whatever 8.1 is. Same type of question, different value. Now this is angle of 35 degrees. So same picture. Here's that box up there. Now you're pulling slightly up. So that being said, when you pull on the stroke slightly upward, does the box slide along the ground? A little change. Well, that's one of the reasons why we use pulley. You end up with 965 pulling like flat across. You're pulling at an angle, so when you throw on cosine 35 degrees, add a little more. Which makes, does that make intuitive sense? It's why we use pulleys. It's why we now we can actually use that. Now, question. Worth of work that costs you your energy. And what is energy measured in? Joules. So what I need you guys to do, work energy theorem basically tells you is that work is measured in joules, energy is measured in joules, because as you do more work, that make sense? Okay, we're almost done here. Okay. Now we also use graphics. Every single thing that we do in physics, we can do an equation for, which is important. But we can also make graphs out of it. And graphs, hopefully I've already shown you that in our 2 weeks together. Graphs are pretty powerful. you are rarely just doing one trial. Usually you're doing 10 or 100. By the way, was it a little bit tedious when we were doing all those trials of recording the stopping and going distances for the thing up there? Right? But unfortunately, that's what science would require is like if you want to do a good job of your experiment, you don't go. You go. I need 3,000. Like goodness, you probably pay somebody to do it all for you, do all the tedious, right? To do it for you. But say you collect all that data. You're right there. Bunch of data for somebody to use it, right? Now, say you collect that data, right? One of the ways we're talking about is plotting graph format. If you plot a graph for this graph will be used as someone but being multiplied by each other. Ever have a formula involving multiple? All of that area. And that would here you could actually then find the energy used. And wait, if you know the work done, if you know how the graph works. So I'm going to do one last example here, and then we're going to call her quits. Here's a graph of force by distance. If you were to find the area of the shape under the graph, what would that have found you? Work. And again, why? Well, because work is force by distance. And your area would have been length times width. Fair enough. Let's try this last example. Of somebody who is doing work. Why are they doing work? Well, because they applied a force, they pushed something, they pulled something, they got something moving. And how do I know it was moving? Because the displacement has changed. The displacement started at 0, which makes sense because if you use 0 force, it moves nothing. Right now, I am applying 0 force to this meter stick. And guess what? 0 force to this meter stick means it doesn't move. I apply a force to it, and it moves. Does that make sense? So here's a graph of somebody slowly but surely increasing the amount of force that they used. They started with no force, and by the time they were done pushing or pulling or whatever the heck they're doing, they finished with 160,000 force by the time they were done. And by the time they were done, this object moved, and this morning we estimated that this was about 115. That's something in the ballpark there. Again, one of the downsides of the graph is that without actually using your computer to know exactly where everything is, you're kind of eyeballing it. That's why we have computers, right? So it looks like it went 115 meters. Here's how I would then solve this problem. If I wanted to figure out, for example, say the question was, how much energy was used to move this object, you might say, well, I don't know energy, but my energy was work. And my work is based on the area of my graph, and my area in this case is a triangle, 1/2 base height. Okay. See how the area of this is 1/2 base height triangle. So my area will then be 1/2 of my base, which I think is 115, and my height, which I think is 160,000. And again, you're going to see this from me more and more as we go on. I don't actually care what the number is. That's not really the point anymore now, right? I mean, you can type it. This is how you'd solve for how much. Let's call it 100. This is now a slingshot. We could take this one step further. I could say, well, hang on. Which energy was used? The energy was 1/2 of kx squared. But if I know the slingshot had a constant of 100, then I can tell you energy could be this formula right here. Things that we're eventually going to oh shoot, okay, I am out of time here. Better wrap this up. Okay, so apparently no clocks in this class are working. Okay, why don't we wrap that up there? So here's the wrap up, and then I'll give you 2 tasks to look at here, since the bell's going in the next 10 minutes here. That's today. So I'd love it if you guys could, on your phone or a laptop, write a brief reflection sharing with me what you picked up on. Do you understand how to type numbers into a formula? That one, hopefully not being too pretty low on that one, but can you type numbers into formulas? Next, you understand that working energy and that energy means what energy is. Put some energy. Well, what kind? Light, heat, sound, magnetism. It's a really hard word to define. We define it more based on what energy can do work. Don't forget there's also then those 4 classes. So if you click on the video here, there's always 5 practice questions for you to do every lesson. Tomorrow I know some of you are leaving early on vacation or whatever, but for those of you who are here, the plan is I just want to give you an hour of ongoing one. We always have reflections and practice questions every lesson. So, if you haven't worked on that tomorrow, the lab that we're in the midst of working on, it's not due. We'll work on it again next week again. But you could spend some time on that. And then there was a practice quiz yesterday, if for whatever reason you didn't work on that. So that's kind of tomorrow's plan. Does that work? Okay, cool. You guys have whatever time we have left, I guess, to do whatever you need to. So if you have questions, make sure you ask. Sorry, I didn't time that very well. I didn't realize the clock was dead. I'd have wrapped up a little earlier. Fire away. Let me just turn off the video first, though. Yes. Yes. Depends on which formula you're given, basically. Yeah. You'd have to... Sorry, I gotta figure out where my setting is for this here. Hang on. it would have to be context dependent that you'd figure it out based off of. Yeah, like you'd have to be clear that either it's a spring or it's above the ground. Yeah, because they both are forms of potential. And theory is energy. There's battery power. That's why it's barely. That works. Yeah, like if you're totally constant.